In this video presentation, I will demonstrate how to analyze shale gas well performance data using Fekete harmony. This particular example comes from the Marcellus. It is a horizontal well with multiple fracture stages. Let's take a look at the data. The diagnostic plot shows several pieces of information, including water-gas ratio, operated gas rate, and casing minus tubing pressure. For gas wells, it is very useful to take a look at where the well may be loading with liquids. We can do that by putting the Turner gas rate on there. The Turner rate is the critical liquid lift rate for gas wells. Also, we can show the Coleman rate. Let's make sure that these are all on the same axis. It's clear from this picture that the actual well performance data is significantly below critical liquid lift volume. So therefore, instabilities in the wellbore may be an issue. Let's go to the Data tab. In the Data tab, we can configure the PVT properties and rock properties. Of interest in this example is adsorbed gas. Since this is shale, we enter in a Langmuir isotherm, and we can use that in the analysis. We could also put in geomechanical properties if they were available, or if we found the need to use them from the well performance analysis. This is a picture of the wellbore. We have a horizontal wellbore. We've entered in our production casing, tubing data, perforated intervals, and we're ready to analyze. Let's go to the Analysis tab. There are a number of different analysis methods available, and many of these are useful for unconventional reservoirs. We're going to start by taking a look at a type curve match. This is usually a good place to start, as it allows us to identify flow regimes in the well. We'll look at a Fekete decline to start with. Let's filter out some of the data points to make the picture look a little bit cleaner. As we can see from this match, the data is still very much transient. The slope of it is shallower than the steepest limiting decline curve, which is the harmonic stem. The next step we can take a look at is the Wattenberger type curve. This is our linear flow analysis. We can see immediately from Wattenberger that the data is not going to match. The reason for this mismatch is probably the presence of damaged skin. If we put the raw data derivative on there, we can see that indeed there is linear flow, as shown by the derivative, but there is significant departure of the raw data from the type curve. And this is probably because of skin. Again, this is just a qualitative diagnostic. To do a true analysis, let's move forward and we'll take a look at the unconventional reservoir module. We'll select gas variable pressure. This is a 4-plot analysis that includes the square root of time, flowing material balance plot, type curve, and then ultimately a forecast. It is designed to get a forecast out of the data as quickly as possible while taking into account all the critical diagnostic plots that go into analyzing this sort of well performance data. Of interest is our square root of time plot. It's going to give us our linear flow parameter. We can change the slope of this line, and everything else is connected to this. As indicated from this plot, we have a significant positive y-intercept. That is the source of our damaged skin, and that indicates that the well is damaged. Our flowing material balance plot is used to move the green line back and forth. That indicates where transient flow ends and boundary dominated flow begins. In this particular case, we have no evidence of boundary dominated flow. It's pure transient linear flow. So we're going to move the dotted line to the end of the data. This is going to be our P90 case. So I'm going to change the name of this to P90. Now we're going to interpret some reservoir and completion properties. We can use this by picking the model type horizontal multifrac with matrix. We can enter in our well length, number of fractures, and the program will calculate a matrix permeability that goes with that, as well as some other well performance parameters that can be used to seed our advanced multifrac model. So now let's go and produce our multifrac model. We can create it from here, multifrac composite. And we can enter in the parameters easily from the defaults. As we can see, it's not matching the data. So what we'll do is fine-tune it by clicking on earmarking FCD and K1 for auto parameter estimation. And the program will now go through a procedure of auto history matching in an attempt to get a best match of the pressures. As we can see, it is adjusting the finite fracture conductivity and the permeability between the fractures. And that's a pretty good match, so we'll stop it there. We can also take a look at what the rate history match looks like for the same case. And luckily it matches the data quite nicely as well. Let's go and produce a forecast from this. We'll go to the forecast and test design, do a 30-year forecast, and we're going to put an abandonment rate on here of 20 MCF per day. And actually we'll go back to the P90 case and do the same thing, just to make sure we have the same limits on everything. And there we go. So now we've got two forecasts, one produced from a simplified method and one produced from a more advanced analytical model. So I'm going to rename this one P90 Analytical. What we can now do is bring a standard decline curve rate versus cumulative plot into place and compare the forecasts. So let's put our P90 analytical on there, and let's put our P90 simplified on there, and we can see there's quite a bit of a difference between the two. And that's owing to the fact that they're using different models. The analytical is probably the most reliable because it's a true analytical model. What I'd like to do now is add a standard decline curve to this. And what we want to do is try and match the forecast from the analytical model. And let's set it up so we have the same limits. So I'll adjust the hyperbolic factor on here in an attempt to get a good match. And it doesn't have to be exact, but we're looking for something that approximates what our analytical model says. This is the decline curve now that we should use for our reserve evaluation. And it's very simple to get that by simply matching our existing analytical model from here. And now we're done.